I've heard this one before, and the answer is absolutely no. It's not.
What's the relief?
We don't have to worry about pennies falling from the CN Tower. You might have to worry about other things, though, but not pennies. So let's take the CN Tower. It has a height of about 500 meters, so it's a really tall tower.
Mm-hmm.
Now, if we were to drop something from that, some people may remember things like kinematic equations, probably like a really, really bad memory.
A distant memory.
So you have the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the height. Now, in this case, we're dropping it, so the initial velocity is not there. So we just have this, and the final velocity is going to be equal to the square root of 2 times the acceleration times the height. Now, if you work this through, acceleration due to gravity, what you find out is that the final velocity is 100 meters per second. Which is like, okay, that sounds like something, but what is that if I can relate it? Yeah, how fast is that? So that works out to be 360 kilometers per hour, right?
So it's pretty fast.
So that's really fast. I'd be scared in a car going that fast.
Yeah.
So that seems like a really fast number, and so you say, okay, well that sounds dangerous, right? But I looked up things like the muzzle velocity of a gun, of a bullet coming out of a gun. And so what I learned is that for a musket, so an old musket, the velocity is about 370 meters per second. For a modern rifle, it is about 1,200 meters per second. So really, this is not that fast, right? An old musket is almost 4 times as fast as the penny that's dropping. The rifle is like, 12 times as fast, right? So the speed is not that high at all.
It's pretty slow.
Yeah.
So you mentioned kinetic energy, though. Is there another piece to this picture?
So the kinetic energy is really important as well, because this is only telling us about the speed, not necessarily how much energy there is, and that is important. So let's think about that for a second. And again, I think that some people may remember a formula that looks something like 1/2 mv squared. Remember that one?
Distantly.
Okay, so the amount of kinetic energy is going to depend on the mass of the object and the velocity. We already calculated velocity and determined that the velocity is actually not that high compared to bullets. What about the mass, right? So again, I did a little bit of research and found out that a penny has a mass that corresponds to about 2.5 grams.
It's little.
A toonie has a mass that is 7 grams.
Okay.
And a bullet has a mass that is about 10 grams. So again, the bullet is heavier, it is faster, and so even the kinetic energy is not that high.
So the penny doesn't come close to comparing.
It doesn't come close.
Okay, so I remember distantly from physics something about drag.
Yeah. So you are absolutely right. So that's one thing that we left out of this, which is what about the air resistance, right? I'm just talking about taking a penny and dropping it down, right? But it's tumbling around, there's air resistance. So the thing is this, if we think about it, if this is our penny, we have, and it's falling, there's a force, a drag force that's acting on it, and then there's a force due to gravity acting on it. And the point is this. The force of gravity is acting on this thing, is making it go faster and faster and faster, but the drag force actually depends on the velocity squared and the area of the object. So a leaf falls very slowly because it has a large cross-sectional area, it's not very heavy, right? And here we have the velocity squared. So this is the important part is the velocity squared, okay? So what that means is that when this is moving moving slowly, right? When it first starts to fall, the air resistance is not very high because the velocity is not very high. But the air resistance goes up and up and up and up and up.
And so does drag.
And so does drag. And at some point, these two are equal. And at that point, we hit what's called the terminal velocity.
Okay.
Now, what's really cool about the penny, if you take the penny, and people have actually looked at how fast does a penny drop, right? Due to air resistance. And I did this, I looked it up. And what you find out is that for a penny, the terminal velocity is 60 to 80 kilometers per hour. So really not
way
that,
less than 360.
Yeah, exactly. It's not that fast.
This is
right?
what it would hit the sidewalk at.
That's the speed it would hit the sidewalk at. Now, just as a comparison, if you're taking a fastball and throwing it like a pitcher, not me, you hit speeds of about 160 kilometers per hour. So that puts that into perspective, right? That's a really small.
People get hit by that all the time.
Exactly. So this is really not going all that fast.
All right.
60 to 80 kilometers per hour.
So definitively, a penny falling from the CN Tower would not kill you.
That's right.
Public service announcement.
So there's one more cool thing about this, which is you can ask the question: how long does it take for a penny to actually reach that terminal velocity? Right? And it would only take about 15 meters of falling before it reaches that terminal velocity. So what that means is, whether you're tossing it from the CN Tower or the top of a 4-story building, it makes no difference. You can actually sit there and like wait for it to hit you and catch it. You'll see it.
Yeah.
So, no worries.
Perfect. Thank you.
No problem.